run through the assignment really briefly. There was a big faculty or departmental or whatever we are, I think, effort to make us get all the specs fully up in the module guides for all the assignments for the entire year. So all the assignment details are in the module guide. I discovered yesterday that I hadn't actually updated what was on the website, so I updated both assignment documents on the website yesterday or the day before so that they match what's in the module guide. So it basically duplicates what's in the module guide. Anyway, to prevent misunderstandings, it's always a good idea to at least run through it, as well as just getting people to read in detail about what they need to do. So, in this assignment, you will take on the role of a data manager, database manager. It doesn't really matter what the title is, but you're an employee of a company, or in this case, a health authority, although I don't know whether I actually specify who you're employed exactly by, doesn't matter. Your job is to design, implement, and document a relational database management system for a study on lung capacity and air pollution in the Kingston area. Your deliverables are a PostgreSQL database with all the data in it, loaded up, a SQL file, just one SQL file. You know, you can put multiple queries in the same file that implement the various use case queries that you're asked to implement. I think there's about 12 of them, 12 queries basically that you're asked to do. And a database design report. While I'm remembering it, you now should be aiming to finish off the used cars practical and be fully good with entity relationship modeling and building and querying a non-spatial relational database by the end of the enrichment week. So you should try and aim to get yourself up to speed. Then when we get back, we do spatial SQL. The level of complexity goes up a bit. So be warned. Spatial SQL is a significant jump in complexity over standard SQL. If you are struggling with SQL still and you go into spatial SQL, there's a danger you'll get left behind. It's not the end of the world. I've got the assignments sort of arranged marking-wise in my head, but certainly last year a number of students didn't actually do really any of the spatial side of it, but there's enough marks that if you do a good job on the aspatial stuff, you can get a pass in the assignment without doing the spatial component. I'm not advising you to do that in any way whatsoever. I'm just saying if you're in the panic mode, that if you get the spatial database design, the documentation done well, you can still pass the assignment without actually completing the spatial SQL. But I would thoroughly advise you to do the spatial SQL. I don't want to scare you, but I also want to just emphasize that that's the position you want to be in by the time we come back after the enrichment week, is to be at least reasonably okay with SQL and building tables and doing queries and stuff like that. The other thing I'd like to say is that when we get back, we do a practical, which is build a, now it's probably my own fault for making it a bit confusing, a practical that uses air quality data recorded by machines that sit by the side of the road and record air quality data every about 10 or 15 minutes, whatever the schedule is for sampling. And the practical involves the analysis of data from about 6 of these machines, which isn't very many, in the sort of southwest London area. The assignment is also on air quality, but instead of using the raw figures coming out of the machines, we use an interpolated. Yeah, everybody understands what I mean by interpolated now? Yeah? No? Anybody not know interpolated? Okay. Interpolated grid, point grid of estimated pollution values. Last year, and I find it difficult to understand how this happened, and I think 2 students out of about 15 tried to do the assignment using the data from the machines that was part of the practical, but not part of the assignment. I mean, it was perfectly clear in my head. I think they just didn't read things properly, so bear that in mind. I just don't want people making a silly mistake and not reading things properly, and you thinking they're using the air quality data that they did they used in the practicals for the assignment. It is a different air quality data set. So just make sure you don't make that silly mistake. Oh yeah. So what you get given is you get some primary data. Well, it's not really. It's invented data. Let's be honest. On lung capacity, entered into a spreadsheet during a brief pilot study. You've been employed, but the study's been going for a few weeks. Nothing unusual there. The data's been entered by a secretary or doctor or whoever, somebody else on the project who's already employed, just entered it into a spreadsheet. It's dirty, it's mucky, it's your job to clean it up, organize it into a relational model in third normal form. So the exercise, once I've talked to this, the exercise we're doing today is effectively taking a dirty table, it's not quite as dirty as the one that I'm giving you, and sorting it out into third normal. Third normal. You'll also be given secondary data on NO2 and the general environment as shape files, which you'll also need to import into your database. Okay, so this is laid out on the spec, so I'll just run through it quickly. So your report, okay, so you normalize your data, third normal form, import all your shape files, then you need to write your report. Okay, so your report consists of various sections. So the first thing is a brief introduction to the application, who it was built for and why, software and hardware used, structure of, and then sort of just outlining the structure of the report. You know, this is, I sometimes wonder why I have to say these things to people, but it's amazing how many people will start without an introduction to their report or essay. Please write this as a report. Don't write it as an essay. Write it as if you're it's a sort of a report structure. So use numbered headings, whatever, bullet points. Don't think you have to write it in an essay structure. It's very much a report structure. So a brief introduction, couple of paragraphs outlining what the report contains and why it was written. I think that's worth 10%, I think, if off the top of my head, 10%. Then you move into the logical design section. So you need to draw an ER diagram that shows the design of your relational model with accompanying text that unambiguously, underlined, very important, unambiguously, defines all entities and their attributes as well as spatial and aspatial logical relationships and constraints. And we'll talk about spatial constraints in the spatial lecture after they. So basically, the design, and remember what I said this morning about the problem between sometimes students' designs being different between what they would like to create and how they think the world understands and what they've actually managed to implement in the database. So your ER diagram should match onto your database. Now, something I should have mentioned in the lecture is that some things that I found, particularly last year, is that people would name the entities differently from the equivalent tables in the physical database. So in the logical model, it might be called people, but in the physical models, it's called person. That kind of simple mismatch loses you marks. Consistency, be consistent, call things the same. wherever possible. And you'll need to describe and justify any design decisions involved in the decision on the design of your logical design. So, for example, we talked about addresses this morning, or this afternoon. Addresses. So, have you implemented a standard for address formats, or have you used your own format? And why did you decide to do one or the other? That's the kind of decision. Keep it brief, but you've got to say, I did this because, or I did this over this because. Okay. Yeah. So so you need to justify why, when you've got choices, why did you implement one thing rather than the other? Keep it brief. So you've got your logical design. And as I say, your logical design should map onto your physical design. Your physical design is obviously implemented as the database. So the tables, fields, and constraints are defined in your database that you create. But you must have also, in your report, you need a physical design section that does things like lists the various fields. So you'd have for each table in your database, you'd have the name of the table, a definition of what the table is about, contains, list of the fields, definition for each field, data type for each field. Okay, and any explanatory descriptive text that you might need with it. Now, as I've said earlier, there's quite often last year there was a noticeable difference between the entity models drawn and the physical designs implemented. So it's and I accept that, that's not a big, to me that's just part of the process of building stuff and learning to build something. It takes a lot of time to do this, so you might not have time to implement everything that you'd like to. The important bit is that I know when I'm marking things that you know that you've done something, you haven't done something, or something like that. So I need to know the differences between the logical and the physical design and why there is these differences exist. So it may be that your logical design includes a section that you haven't actually had time to implement in your physical design. Well, make sure you point that out. Describe and justify any design decisions when translating your program. So why did you choose this particular data type? Okay, it's usually straightforward, and you could make some statement like at the beginning that all data types were chosen to minimally, or take the minimal amount of data while space on the disk while including extra data. But then there may be occasional fields where you feel you do need a little bit of extra explanation as to why you did it this way rather than another way. So constraints, things like that. We then move on to the use case examples. So use cases are just examples of how the system might be used, and you have to demonstrate as the developer that your system actually delivers those needs. So I think there's 12 different queries and one map to produce. We're actually going to see a map when you get back from the enrichment week. That'll be exciting. So you've got to, in your report, I'd like you to put in your queries and their solutions. Okay, so make sure you tell me what the name of your SQL file is that contains the queries, because I'm actually going to be running them on your database to check that they actually work and do return the right results. Your queries that you write should be as concise as possible. We've gone through the fact that we can write the same query in different ways. Well, write it in the minimalist way you can. So they should be concise, and name the columns returned suitably. So give them suitable aliases rather than just giving the default database names, which aren't necessarily the most, particularly for calculated fields, aren't necessarily the most informative. If your query returns many rows, then just show the sort of first few rows in the report and then say return 65 rows or something like that. Comment your SQL. So your SQL file that you're returning, make sure you comment it. So it says query number 1. Tell me what the query does. Okay, you're repeating. All you're doing is cutting and pasting the query out of the assignment document into your report. But for example, last year I got queries in a query file. I maybe got 8 out of the 12 queries. They weren't even in the order that they were in the assignment. So I would have to work out which query in the list in the SQL file matched onto which query I was asking. That just annoys me and loses your marks. So make sure it's really clear what goes on. If you can only if you've got a solution that you're going to get marks. So I can give you a list of how many marks for each query if you want, and I will do that. Basically, the harder the query becomes, the more marks you get for completing that query. However, if you've got a partial solution, or a solution that you think is sort of some of the way there, then put that in and note that it's a partial solution. And if you know what you would like to do to complete it, then maybe put a little note in and say, give me another hour and I would have done this. And you'll get partial credit, Just because it doesn't do exactly what's required, it doesn't mean that you don't get some marks. And 5% of the marks are for the quality of commenting and the formatting neatness of the SQL queries in your SQL file. So be nice and tidy, nice and easy for me to read how the query operates. And then at the end of the sort of summary, 10%, just a short summary and future development. So identify and critically evaluate any problems that you can see with your design or its implementation. So there's a few things that are actually quite difficult to implement. So one of them is I ask you to implement family relationships, who's the brother or the mother or the father of various patients, so that we get some idea of obviously lung capacity and propensity to lung capacity and its relationship to pollution may be genetically controlled. So we want to know the relationships between people. That's actually a really hard thing to do in a relational model, and I would only expect the A+ students to actually come up with a good solution for that. So if you've only got a partial solution, well, I'll make sure you identify that and explain what its limitations are and what you might do in the future to improve that. If the database that you managed to create is only half finished and not suitable for purpose, then make sure you explain that. And then you may have, and then the final thing is to consider, identify and prioritize future system development. So one thing is things that you haven't implemented that you plan to implement, but there's all sorts of other things like, okay, we're going to deal with interfaces and things next year, but how would you consider somebody who is, basically a clerk, office manager or office person has got to manipulate and use this database and enter data into it. So you might want to consider what are the other things that need to be done to make this database actually usable by people in the thing. Not in great detail, but hopefully you can put some general pointers. Okay, some guidance. Okay, so we've got this problem about the mismatch between reality, how things are in the real world, how you've depicted them in your logical model, and how you've implemented this in your physical model, this implementation gap, basically. The bottom line is make it clear. If I've got an ER diagram, make sure I know whether it should, as I say in the instructions, it should be mapping onto the physical model. And I'm going to be checking them, eyeballing them up again, making sure that all the fields in your logical model have been implemented in your physical model, and you'd be surprised how many aren't. I make sure that they're named the same. I make sure that the relationships have been correctly implemented. So make sure your logical model matches onto your physical model. But if you haven't managed to, if they're logical parts that you haven't managed to implement, then make sure you highlight those and you identify those in some formal fashion. You could even have two ER diagrams, the world as it is and the world as it is in my computer database. You could do that, but usually they're just minor superficial changes. You've not implemented one or two tables or something like that. So I leave that entirely up to you. You've either got the option. Now, okay, the other thing is that there is often a lot of overlap between logical and physical models, okay? In the logical model, you've got your entities and your attributes, okay? And a lot of the time they map onto single tables, yeah? And then you've got your relationships, which may be turned into tables or may not be turned into tables. Clearly, if most of your entities get turned into tables, and you've got a table that describes the entities in your logical model, defines the entity, defines all the fields, the attributes of the entity, and then you've got a table that is effectively the same as the entity. You've just called it a table instead of an entity, and they've become fields rather than attributes, and you've just added a data type on. Clearly, it's pretty pointless to have one table which is a logical model and then a physical model table which has one extra column. So if your logical model matches your physical model quite closely, you perhaps want to compress your logical and physical sections into a single design section. I kind of try and explain this in the assignment remit. To a certain extent, it's judgment on your part whether you want a separate logical section, a separate physical section, or whether you want to combine them into a single section. I leave that up to you, and if you want, you can come and talk to me about whether it's a good idea or not when you're closer to the time, if you like. So we haven't dealt with spatial entities in ER models. I'll talk about whether in the spatial after the enrichment week, I'll talk about that. Basically, there's probably not a lot of need to put the spatial information into your ER model. It's mostly an aspatial ER model. In fact, almost entirely a non-spatial ER model. Secondary data and logical and physical models. Okay, so the question is, okay, I give you data that I've downloaded from the Ordnance Survey, roads and rivers and towns and the buildings and things like that. Should that be in your logical model? My view is that there's no point in including it unless it's involved in some kind of constraint with your primary data. If it's just a standalone table of roads, what's the point in putting it on your ER diagram? Because it doesn't connect through a relationship with any other of the entities in your system. However, some people put standalone tables round the outside, not connected to the main. That gives you a complete overview of your model, but maybe means you've got 10 unconnected tables spread around your diagram, making it more complicated. Now, if completeness versus complexity, again, it's cost benefit. It's up to you. Do you think it helps to have all the data there on one sheet, or does it make it more confusing? It's a design decision again. So, secondary data. I wouldn't bother having a table with the secondary data fields in, because all I'm doing is copying what's probably on the Ordnance Survey page where the define of the Meridian data set is. So the Ordnance Survey will have a table there that tells you the definition of the entities and the attributes of the entities. There's no point in copying that whole into your report. Just provide the link address out to the metadata that's available online. So secondary data, if it's available and described online, provide a link. Don't bother making copying that information into your design document. Ambiguity. The world is full of ambiguity, except in computers, where it has to turn and solidify into some kind of exactness. So you will find ambiguity in the data that you've been given. There is potentially ambiguity in the definitions of data. So you have to deal with that ambiguity. Now, dealing with ambiguity is kind of difficult, and it depends on who the buck stops at, so to speak. So you can come and ask me, you can say, look, I found this in the data, I don't understand that, or that sounds a bit odd, I don't understand, you know, I'm a bit confused, is it that or is it that? Well, you can come and ask me, and then I'll say, okay, I'm your boss, I'm going to tell you that it's this, or whatever. So bear that in mind. If you find ambiguity, you either go and ask, if it's important ambiguity and it's causing trouble, you can ask questions of the person who's in charge of the project, me, okay? Other ambiguity you can just kind of cope with. For example, maybe there's two options, two possible solutions or two possible answers to this bit of ambiguity. It's either A or it's B. And maybe you can write two queries, one that gives me A and the answer to A, and the other one that gives me the answer to B. Then why not just give me both and point it out that it's an ambiguity in the document, okay, rather than coming and asking. So you've got the choice there. You can either just absorb it into your document, recognise it, highlight it as an area of ambiguity, or you can actually ask me to try and for some kind of definitive answer. Family relationships, I've already mentioned. It's the hardest part probably of the whole assignment. Don't feel that you're failing if you haven't managed to implement a perfect family relationship model. It's not easy. Final thing, I have a good idea. So developers are quite good at coming up with good ideas. Well, we all are, you know. I've got to know, why don't you do this? Okay, but your job here is to implement what you've been asked to implement, not to decide what the use cases actually are. You've been given use cases, your job is to implement the database to meet those use cases. Your idea may be exceedingly good, but it's not your place to make a decision to implement any idea that you have. It's what you stick up in the summary report. You could do this, you could do that. This would be an advantage because. Okay, so having a bright idea, don't go doing anything with it except recording it, passing on to the people who then make the decision, i.e. me. Although no decision will obviously ever get made.